This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs. Also, make sure to check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube.
Good evening and welcome to another evening of City Arts and Lectures. My name is Michael Krasny. I'm the host of KQED's Forum, which you can hear weekday mornings from 9 to 11, 88.5 on your dial. First of all, sincere thanks to all of you for being here. There's a lot of competition tonight. I want you to know that the Giants are ahead 7-0. And despite the fact that some people think this is a pennant race, it's the seventh game to decide who the winner of the National League pennant is, and despite the fact that there's the last of the presidential debates this evening, we're talking about the beginning and end of the universe. That's far more important. And we have the good fortune to have two Nobel Prize winners with us this evening. Let me just tell you who they are, and then we're going to have a video, and then they're going to come out and we're going to have a conversation. George Smoot, they're both, of course, at Lawrence Berkeley National Laboratory. George Smoot is a 2006 Nobel Prize winner in physics, which he received with NASA's John Mather for studies of the cosmic microwave background, which was performed in 1991 aboard a NASA satellite, the Cosmic Background Explorer. We also have with us this evening Saul Perlmutter, also a Nobel laureate in physics, 2011. He's also the co-founder and leads now the Supernova Cosmology Project, and his Nobel was for the discovery in 1998 of the accelerating expansion of the universe, with half of that prize going to Brian Schmidt and Adam Rees of the High Supernova Search Team, the SCP competitor. So we'll have the privilege and the pleasure of conversation with these two gentlemen this evening, and you'll have an opportunity also to ask questions and get involved in the conversation later on in the evening. First of all, though, some of you might be worried and on edge about the Mayan calendar, which is predicting an end to the world as we know it on the 21st of December. Our two Nobel laureates, I think can be somewhat reassuring, at least I hope so on that point. But there is something that we share with the Mayan culture, and that's the connection of curiosity about what's up in the sky, in the night sky particularly. And Berkeley Lab has produced a short video that explores the human connection, and we'll play it for you now.
Humans have always been interested in the sky. At night they go out and looked at the sky and seen the stars and wondered what were they and how did it have to do with their own lives. As people looked at the night sky and wondered and started studying more, they built more tools, but they always used the naked eye. One of the groups that was very good about doing that were the Mayans. The Mayans were very careful observers. They observed over hundreds of years, and they built up a very systematic set of knowledge. They integrated it into their daily life, tied it into their stories of what life was like, but they also wondered what else they could learn.
I think there's a common human curiosity and just desire to understand the world around them. The patterns of the seasons, how the sun moves across the sky, phases of the moon. The Mayans were very into phases of Venus as well. They knew an awful lot of astronomy. It's human curiosity to understand the flows in the world around them, the contents of the world around them. And that's what we're doing today as we look out into the universe. We want to understand the galaxies, the stars, how did the stars form, how did the elements come from the interior furnaces to form the planets, to form the elements that make up our own body. It's a continuous pattern of trying to understand the world, and that's what cosmology is. Cosmology means the same thing to the Maya that it really means to to the scientists today.
When you hear about the Mayans and their the calendars they constructed and the entire calendar systems that they had built, it really feels very familiar. You feel like you're seeing yourself in people who really were trying to understand a world around them by careful observation, and then they collect the observations, they understand it mathematically well enough that they can make predictions about what will be coming up in the future and actually make plans based on those predictions. It all sounds so much like what we do ourselves when we're trying to understand the universe around us. And this curiosity, this desire to understand in a very analytic way, and then turn it into something that you can actually use, I think feels like something very human.
We can see this connection across the ages. Here we are at the Mayan site where for hundreds of years, thousands of years, people have come, observed the sun, observed the sky, and we're doing the same thing. You have the same feelings that they did. And we have the same wonderings, except now we're wondering about an even greater part of the universe. It's a shared passion for understanding the world and just the human experience of looking at the sky and understanding what it looks like and seeing the same sky the Mayans saw.
The architects at Chichen Itza had encoded into their own buildings these ideas that they knew would go beyond their own lifetime. Building their calendar, for example, into the steps around the temple of Kukulkan, or building their sighting tubes into the caracol showing the link to Venus. That's something that would have spoken to Maya outside of the city, to people who came after them, and it's the kind of thing that we're still interested in today. So they were encoding within these buildings knowledge that speaks across culture and across generation. And I think that's something that can be very exciting for us to participate in.
The sort of structures that we see around us here at Chichen Itza show how that curiosity basically turns into science through the observations that you make. The Maya were experts at observing the path of the sun across the sky, aligning their architecture so you could understand when is the summer solstice, when is the spring equinox, which of course had very immediate consequences for planting of crops, harvesting, and so forth. Today we go beyond that. We still use the observational techniques, but now we're asking, you could say, much broader questions. So instead of about our everyday lives, we're trying to really figure out how the world around us came to be. Where did the Earth come from? Are there planets around other stars, which we've now learned that in fact there are many hundreds of those. Understanding where did the stars form, the galaxies. Trying to understand the force of gravity.
I bet that the Mayan scientists, if they were here today, would have loved to be part of this project of actually going out and measuring the history of the expansion of the universe to predict the future of the fate of the universe. And they would have been, I think, just as tickled as we were to discover that the universe was doing nothing that we expected. We had thought that we were going to find out if the universe was coming to a halt and someday going to collapse, the end of the universe. But what we actually measured was a universe that's not slowing down. And in fact, it's not going to come to a halt. The universe is not coming to an end. And one's first impression is that that means the universe is going to last forever. It's going to keep on expanding forever. Now there's a little footnote here, which is that it's not just not slowing down, it's actually speeding up. And we've got no idea why. So the next job of the scientists, and where everybody's diving into this, is to try to explore this question. If we can figure out why the universe is speeding up, perhaps that will give us another chance to revisit that question. Okay, but then what really is the fate of the universe?
Those are new things we wonder about, just like the Mayans wondered about the night sky. We wonder, how can we understand that? How can we study that? What does it mean for our future? What does it mean for the world around us?
Ladies and gentlemen, please kindly give a warm welcome to Saul Perlmutter and George Smoot. Let's begin by talking about the Mayan civilization and the connection you gentlemen feel. I mean, there's the curiosity, of course, about what's out there, but there's also a link and a connectedness that has to do with innate discovery and searching and so forth. You really feel that connection?
For me, it was, you know, I was going there to give a talk. So you didn't see in that, but I had the good fortune to be allowed to be in the ruins after dark and to see the stars arise over the Chichen Itza thing, and then give a talk about that and how it relates to modern cosmology. And so I did a little research on their calendar, and I even felt closer to them than I thought I did, because they literally have been keeping records for 300 years. And they have been improving their measurements and lining their, you know, Chichen Itza is a high point. They line their monuments up so that on the solstice, the shadow of the sun goes down, walks down, and makes a serpent, right, down the stairs. And it counts the days of the, you see the days counted up over time. So there's a big crowd that comes there for that time. And you know they had ceremonies, so they mixed their life and their religious cultures with their scientific observations. But the thing that you identify with are their astronomers, because they are people who are making observations over hundreds of years and systematically improving and getting better. And some of them were just because they wanted to know things, and some because knowing when the solstice was and knowing when Venus was around tells you when the rains were going to come. That's when you plant the crops. So it was a mixture of stuff that turned out to be a really useful society, and the desire to really know stuff. And that's how I think most scientists are.
Yeah, it does explain certainly the scientific method in many ways, but how much should we give stock to this December 21st date? Saul, how did they come by that, you know?
My understanding is that it's a misreading today of what was just simply a decimal place system, and that they, well, not decimal, it was different base, mostly base 20. But we were just actually about to use up one of the digits, and we're about to go to the next digit, and that was why the calendars were written the way they were. And I think some misinterpretations led people to believe that meant that was the end. It's as if when we reached the year 1999, that was going to be the end of our world. Of course, I don't think most of us were that concerned really that 2000 was going to be something very different.
Well, let's actually, I want to save a little bit about the end of the universe and concentrate first on the beginning of the universe. Actually, George, you had something you wanted to add here, though?
I was going to add something to that, because I also visited Teotihuacan, which they inherited some of the calendar information from, and they had a short form calendar which sort of tied to human life in a regular cycle kind of thing, and then a long form calendar, and this is the fourth cycle of the long form. So it's like getting to 24 hours and ticking over. It's not anything special like that. But the other thing that was interesting, at Teotihuacan, they would build a new level to their city, and they would switch from men rulers to women rulers. So, we don't have the same system anymore. I'm not exactly sure why they did that. but it's kind of interesting how societies did it, and how they tied looking at the heavens to how society itself functions. And so that's the question of, are we going to do that again? Right?
Do you have the answer?
I don't know. Oh. We'll talk about the future of the world.
Well, let's go back to the beginning, though, because I'd like you to begin, George, by explaining what you discovered with your research about the Big Bang and the incontrovertible nature of the Big Bang, particularly in light of the fact that, as you know, I believe I wrote a book about agnosticism, and Stephen Hawking said, I was an agnostic until I realized that gravity preceded the Big Bang, and now I'm an atheist.
He was also fighting with his wife. So there are personal aspects in it.
Well, talk about what you discovered, because it really was. I mean, it's been called, Hawking called it, the greatest discovery of all time, maybe, in terms of the ability to measure the Big Bang and to be able to actually quantify it.
Well, that also helped him sell his book at the time. So yeah. he had a vested interest, but he was very nice about that. What I worked on, a lot of my early life research and middle life research, is to study what we now call a relic radiation from the Big Bang. That is the light that's left over from when the universe is very hot and very dense, like at a time much hotter and denser than the sun. And first to show that it was the relic radiation, and then to actually use that to make essentially a picture of the embryo universe. And that picture of the embryo universe revealed that the universe is remarkably uniform, almost perfectly uniform, but has variations at a part in 100,000, which is 200 times smaller than the variations of the surface of the Earth.
not uniform, but you said at one point it was much simpler than you had ever
It's
imagined.
much simpler. It's a beautiful sphere, you know, the uniform in all directions, except there are these very tiny variations, and those are the things that make the things we think are interesting, the clusters of galaxies and the great walls of galaxies, the beautiful pictures you were seeing there, and eventually fragment into stars and nebulae and so forth. And so what the measurement was that everybody was amazed at was to see how beautifully it fit to the model of the universe, but how there were the seeds for what were to develop later in the universe, and that you could model and extrapolate to the future and explain why you see stars and galaxies and eventually planets and so forth. And so that's a very exciting time, right?
And it was also exciting for you, Saul, to really, in a counterintuitive fashion, discover that the universe was expanding. I mean, in fact,
Accelerating.
Pardon?
Accelerating.
Accelerating, yeah.
Yeah, Hubble found it was
But
expanding.
I mean, certainly you went into the research like many at that time thinking this was not the case.
What we knew at the time when we started, what we thought we knew was that the universe was expanding. Hubble taught us back, 1930 time frame. But ever since then, the big question had been how much would the universe be slowing down in its expansion? Once you know that it's expanding, you tend to ask, well, won't gravity slow that expansion down? And people had assumed that if you slowed it, if there's enough stuff in the universe to attract each other, then the universe would slow to a halt someday and might come to a halt and then collapse. So we had the fun project, we thought, of setting out to find out how much it was slowing down and seeing whether or not it was slowing enough to someday come to a halt and eventually come to an end. I mean, I couldn't actually imagine a better project, but it turned out that it was better because it was not slowing enough to come to a halt, and in fact, it wasn't slowing at all. It's actually speeding up. So that was the big surprise. And so now we have an extra mystery in our story because we don't know what's powering this acceleration. Why would the universe be expanding faster?
Well, we do know that roughly by your estimates and others, close to 3/4 of what we call the universe is dark energy, and that's something we don't even understand really, do we?
No, in fact, when we say that 3/4 of the universe could be dark energy, that's just assuming that you give the simplest possible explanation that there is some energy that's powering this acceleration. But since we don't yet know any of its properties, we don't even know whether really it is an energy. We call it dark to represent our ignorance, not to represent its color, that sort. And in fact, it could turn out to be that's wrong. It could be that it will just be that we don't quite have Einstein's theory of general relativity quite right. And once we really understand gravity, maybe that will be the explanation. So it's one of these great cases where when you learn enough, you start to realize how little you know, and how much more there is to discover.
But we are seeing, I mean, cosmology has become really a science, whereas, not that long ago it was certainly not a science. It's more a philosophy, let's say, or even a theology,
Now, people used to say that if you got something right within a factor of 10, that was really great for cosmology. That was, doing precision. But nowadays, actually, we're doing measurements that are good to 1% in cosmology. And I think George's work was sort of the first moment that kicked that whole new era off.
So I started using the phrase, now we're going to enter the era of precision cosmology, and I got a lot of grief from our colleagues. But in fact, we've got there because we've had not only the original satellite where we made the discovery, we had a second satellite, WMAP, and now we had Planck, and the Planck data is about to come out. We've made these substantial incremental improvements in our understanding and inspired other measurements. And so we're actually doing quite well in trying to understand the universe around us.
Well, I've got to ask you, because I was up on the stage with Brian Greene and was hearing all that hypothesizing about string theory. Where does string theory fit into this for you gentlemen? Because it's not exactly a precise form of measurement.
Well, I'll be curious to hear what George thinks, but I think most physicists who are not string theorists are relatively dubious. They feel these are really smart people, and they're doing amazing mathematics. But so far, string theory hasn't yet been able to make a prediction that you can actually go test. So it could be that it's very accurately describes these mathematical structures, but it doesn't help us understand the universe. But we don't know for sure. At the current moment, I'm a little bit dubious about what we'll find because string theory is originally we thought would not work with an accelerating universe, but it turned out that once you knew that the universe was accelerating, then it was able to save that problem by inventing the multiverse solution, where, which some people don't consider much of a save.
There's a parallel universe right now where the Giants are losing, right?
Well, precisely.
No, I don't agree.
And what have we learned, George, maybe talk about what we've learned from the colliders now, because that's a great deal of information and expansion of our knowledge.
I think that's very exciting, and I've been visiting CERN for many years because I actually think in the end, high energy physics and these great accelerators and the beginning of the universe are going to be intimately tied together. And in fact, our understandings and mysteries in cosmology are deriving a lot of the research programs in high energy physics because you're wanting to understand what's the dark matter, right? And you're wanting to understand where mass comes from. That's why people get excited about this Higgs-like particle, that it may actually explain to us what the mechanism is for how we break the symmetries, but also how we give particles mass. One of the problems if you have an expanding universe, just run it backwards, right? If you run it backwards far enough, we think inside of our visible horizon there are about 100 billion galaxies with hundreds of billions of stars in them each. And you squeeze them in, it turns out it's mostly empty space. So if you bring it into the inner solar system, that is out the radius of Jupiter, you can pack all the protons and neutrons together for the whole observable universe, and they fit just inside of Jupiter's orbit. But we want to go back further than that, and so you have to understand what happens when you squeeze protons and neutrons past nuclear densities. And they got to free up, they got to lose mass, they got to get point-like, so you can squish them down to the beginning of the universe, so that we can eventually get to string theory or something like that. And so that's where the particle physics accelerators are taking us. They're taking us past the point of the kind of nuclear physics into figuring out what happened in those first few fractions of a second. When the universe was much simpler, it was a sort of a thermal, it was like a soup. And so we're hoping to understand the entire history and story of the universe from the moments of creation right up to the present day, and then predict confidently, that we'll make it through the, 12, 21, 12, right?
We hope. Huh? But if
I would bet money on that. I'll hold your money.
if there's this continual acceleration, Saul, and it may be infinite. I think the assumption is it is infinite. Where does entropy come in? Because that's a law of thermodynamics. Isn't that a real law of the universe, physical science?
Well, it doesn't necessarily have a problem with the issue of entropy for several reasons. And one is that the questions of how much entropy you have in the universe, which is basically a measurement of disorder and order in the universe, those really apply in a closed system. And it's not clear what you're talking about in terms of a closed system when you have an infinite space to work in. We often talk about the universe, the visible universe, as this sphere that we see that George is referring to. But that's just the sphere that we get to see in the lifetime of the universe. There's nothing magical about that edge of that sphere. If we happen to be, your sphere is a little bit different from my sphere in terms of what you get to see looking out into the distant past. So the universe, as far as we know, could well be infinite in all directions. And then these rules that we apply to contained systems become a little bit different.
But this is the physical universe as we understand it. There may be, particularly when we talk about things like dark energy or dark matters, things that are beyond our ken, beyond our comprehension.
But our assumption is that they won't stay beyond our comprehension. I think we really think that we have a fighting shot at understanding it. We just have to do the measurements, and we've barely begun, actually, exploring what the properties are of the dark energy, for example. We've had a few more years on dark matter. We should make sure people understand that those are two separate mysteries that we're facing. The dark matter actually acts as an attractive thing that does hold galaxies together.
Forgive me, I like to think in percentages like Romney 47. There's 74 for dark energy, 24 for dark matter, right? So we've got like about 4 of what we understand.
Exactly right. So, but we're 4 is a good start. If we managed to get 4, I think. But I think we have learned a lot about what dark matter isn't, and I think we have a chance at getting what it is. For example, we're hoping that maybe these next years of accelerators results from the accelerator at CERN, the LHC, might give us some information there. And dark energy, we've just begun the next generation of experiments, which. I'd say give it a few years first to see what we get.
Are you as optimistic, George?
I'm optimistic, and I want to say it in a different way. So I used to have this theory of ignorance, which is a measure of your progress. And unfortunately, a certain vice president ruined the knowns and the unknown knowns issue, right? I mean, there's a lot of stuff out there we didn't know until we made discoveries and pushed the boundary of knowledge out. But if you, in the beginning, when you're getting a bigger volume, the area increases faster than the volume. So your knowledge, things you know, goes out to this boundary, and then those are things that you're ignorant about because you don't know them. There's stuff out here where you've never even gotten to. And I just realized when Saul was talking about the entropy, there's another way you can talk about entropy, and that's information loss. And so when the universe is accelerating, things that are inside our visible universe go outside, and we cannot learn about them after that. So we have this apparent horizon around us where things disappear, and we can never see them again. We lose information about them. And if you count that as entropy, which is also the equivalent of entropy on a black hole, which is the one thing string theory claims they predict, you find that dominates the ignorance of the universe is dominated by the boundary on the outside, just like my model, except it's very spherical compared to my model, which progress in science is kind of irregular.
But forgive me, I thought the universe is flat.
The universe is flat, but there's a horizon beyond which you cannot see, you can't get information from, right? And that on that boundary, you're having this thing that represents your ignorance, the information that passed out of your ken, or the stuff that's already out there and you can't know about it. And that actually dominates the universe by orders of magnitude. And then the black holes, where stuff has gone in and got out of your axis, they're the next thing. And then finally, it's the light and the stars, right? The thing that we think of as the waste heat and the waste energy that we usually think about when we talk about entropy. And those things are increasing. The laws of thermodynamics hold true in the end. Turns out there's this deep connection between gravity, which we thought was a fundamental theory, and thermodynamics, which we thought was a statistical theory. They're, statistical mechanics. They are actually very deeply tied together. And so it's not such a surprise if you step back and take a look at it. But it's kind of amazing that the universe obeys this information. And the idea that the universe is a giant computer, or a computer is a giant universe, or whatever it is, those ideas work amazingly well. You do these calculations. And so we're learning these amazing things about the universe, which hopefully will teach us about how we're going to do, things in the future. And it's kind of an exciting time when we're probing these things. And then what Saul hasn't mentioned, if it's dark energy and not some form of gravity, we don't know. That may go through another phase transition and turn around and become attractive. And then, till we understand this, we don't know what our real long-term future is, till we know whether the dark energy is going to stay in its present form or going to convert into something that may be attractive again.
Remember what Eric Idle of Monty Python said, there are two forces in the universe, there's gravity and levity, and I always sort of fancied that myself, that dichotomy. But how much in this connection, Sal, does space exploration play a role? I mean, particularly in light of the fact that we've had to cut back, NASA has to get leaner and all of that. How much do you see it playing an integral role in terms of getting to this kind of research and getting the answers we're looking for?
I mean, these sorts of questions you can approach using a lot of different techniques, but it is true that some of these measurements that we need to make to understand things like dark energy are best done in space. And so it does slow down the progress. We certainly saw, for example, in just the last decade, that there was a moment where we were about to do this next generation space telescope that would have given us a chance to already today have the next measurements of the dark energy, and that got postponed. And so I'm optimistic that we'll get there. Of course, it just makes you a little bit less optimistic about the timescale as you watch the budgets, debates.
How optimistic are you about the survival of the universe, both of you?
I think it has a good chance of going on whatever we do, but it's. I do think that George makes a very good point that it's very difficult to make predictions unless you know what you're already seeing. And since we haven't yet quite figured out what it is that this current acceleration is caused by, I think all bets are almost equal.
Makes it impossible to predict, and yet, George, I think you have some predictions in your pocket, don't you?
Yeah, I am pessimistic, although I hold this one sliver that there might be some change in the dark energy, and let's just make some change so we can think about universe forming, that is, fixing it so it'll be okay for life. But if you look, the long-term prognosis for any individual human being is not usually that good. Right? Nobody's lived forever so far, and it'll be a while before that happens. And if you look, because we have the increase of disorder, people break down and age and so forth, machines do too, that you kind of know that if you don't have some source of low entropy and some source of energy, that you can do that. It's going to be that way. So we've had a tremendously good run with our sun. We've had 4.5 billion years of almost uniform radiation, keeping the Earth at a pretty constant temperature over all this time. But in about 1 billion years, it's going to get warmer. And that's because the sun is burning up the hydrogen in its center and leaving behind helium, and that eventually poisons the center of the sun, and it has to start burning further out and burning hotter, and therefore it'll swell up and be cooler on the outside, but get closer to us. So, and there's going to be global warming. Even if we fix the global warming, there will come in 1 billion years serious global warming. Now, 1 billion years is a long time. So we're not going to worry about this personally, even if we have immortality, because then we'll take this seriously and we'll go and fix things up. But in about 1 billion years, the oceans will start to boil, right? And so that's not so good.
Are you on board on this, Saul? As grim as
I'm just more of a natural optimist in this kind of thing. I mean, my guess is that that the big test is can we manage to solve the social problems of our day, because I think if we manage to get to the point that we're all round in about 1 billion years, I'm betting that we'll figure out what to do. That we'll have we'll be off colonizing some other part of the galaxy,
all
which
right.
is a little
well,
further
I'm
from the
not
sun,
done yet. I still got to argue. Okay.
Okay.
So in you really got to do this. 3.5 billion years to 4 billion years, the sun is going to start burning a helium core and have a terrible flash. And if it hasn't lost enough mass before that, it's going to burn up the Earth. Right? If it loses enough mass, the Earth will move out further enough, and it'll only be a cylinder, a crispy cylinder. And and then the sun will start shrinking and become a white dwarf, which is hot, but small area, so it doesn't heat up so much. And then it'll become a brown dwarf, and it's going to be really dull around here. So we're going to have to go to another star. But if you go out, like 100 trillion years, right? Every star in our galaxy will have burned out, and the ones that you scrape together raw material, you're still not going to have enough, right? So now you got to think, are there any other galaxies handy? But his discovery that the universe is accelerating tells us by the time we get to then, there's only going to be one galaxy in our horizon, namely us plus Andromeda, and Fornax is going to merge with Andromeda, and we're going to merge with Andromeda, and there's going to be one galaxy. That's it. So we're going to run out of stars, so we got to think about, taking energy out of the vacuum or something. Now they did that in, certain science fiction stories. That's going to turn out to be trickier, right? But I think if you have billions of years, you can probably, do science research if you get, if there's federal funding. But so I'm pessimistic because, unless the universe starts slowing down and stuff starts coming in on the horizon so we can gather resources, it's pretty bad. And the chances for life surviving past, a few trillion years it's really getting slim.
I have to change my whole...
Right. Now, if you were Woody Allen, you would be in angst right now, right?
Well, actually, I'm thinking of a poem by E. Cummings that ends, "There's a hell of a good universe next door. Let's go." Saul, you want to refute someone here?
I don't know. At the trillion-year thing, I'm not sure I should bother, but I will.
It gets worse. I have more in my pocket.
But I will say that the favorite lecture I ever heard, I think, was the one when I was a graduate student that Freeman Dyson gave, where he was actually trying to estimate, assuming that we can do whatever we want, just following the limits of physics. So we can pull together energy from whatever sources we can find around, et cetera. He was trying to calculate how...
See, that was before you discovered the accelerating universe. That made it harder.
It's true, but I was going to get there. So he ended up trying to calculate how many thoughts we could have as a civilization. And as long as you still have an infinite number of thoughts, you could power an infinite number of thoughts, that's an infinite life, for a civilization. Now, at that time, he could get an infinite number of thoughts, which was when the universe was still slowing down. Then the debate came up again after we discovered that the universe is accelerating. Does it still work? And it turned out that, very interestingly, he still could get it to work, but there's another group, this was Lawrence Krauss and blocking name, where they disagreed, and the whole thing boiled down to the question of whether or not thoughts had to work digitally or analog.
Right. So you computer guys, you Silicon Valley guys, you know, do you think that all thoughts are rigid digital, or everything quantized? You know, random quantum computer, are they all digitized or are they analog? Right. And it's not obvious, but physics usually tells you that it's going to be quantized, and there's going to be a finite number of states. But it's a very good argument about what is life, you know, what is experience, what's culture, and it really makes you ask these basic questions when you're facing your complete demise, and even not just your body, but your avatar too. You know, it's nothing sacred. You know.
Well, you mentioned the sense that, well, I'm just thinking a trillion years. I'm trying to get that in my head.
You're not going to worry about it right away.
No,
your investments won't last that long.
It's like worrying about the national debt, I'm sorry to say. When we go back to the beginning of the universe, though, and it is, as you say, George, in some ways simple, despite the fact that we know so little about it, it keeps turning out that Einstein is right, though, about most things, isn't he?
Right. That's one of the things that's interesting. So far, Einstein has been right, and even when he made a mistake, he made the simplest and the best possible mistake. Mm-hmm. And you have a very simple view of what general relativity is, which is that the curvature of space-time is equal some constant times the contents. And you've got to get the units right. And that's one of the stupid constant between those things. That's all the physicists is getting the constants out.
What you guys call the cosmological constant?
Well, the cosmological constant gets put on the curvature side, according to Einstein, but according to the dark energy side, you just move it to the side and it's morally equivalent.
It's a shell game.
Right. But it's philosophically very different conceptually, right? Because then you can actually have it change and be different whereas if you put it as a constant, it's by definition, right? And so he really got things very right. But one of the things that we're trying to do is, when we're now using the cosmic microwave background plus data from other experiments, we're trying to do measurements where we're measuring the parameters of our best fit model of the universe, but we're also wanting to test, is general relativity right? And so some of these searches we're doing for the dark energy or the fits for the general parameters of the universe, we're actually trying to do tests. Is it modified gravity, right? We have to modify. So we're testing that. So far, Einstein, won, universe 0, right? But it's still the second inning or something. So, but he was a pretty smart guy.
Speaking about smart guys, I'm interested in finding out, both of you have been professors for a while now, dedicated classroom teachers, and you must have thought about this whole question of how do we make physical science and how do we make physics not only more interesting, more comprehensible, but maybe even more inspirational, because it really is a fascinating field, and it's obviously been fascinating to you your whole lives. Some wisdom on that, Saul?
I mean, my feeling is that the way that science has been taught sort of has been following the way in which we learned about the science. And it's not necessarily the best way to teach. I mean, right now, in order to do the interesting stuff in science, you have to take so many years of what, to many people, is just not the fun part of the story. And I think in some sense, it might be much more fun to teach it the other way around, where you actually give a really good problem about the world that you actually live in, that you'd like to solve, and you say, okay, let's learn all the physics that we need to solve that problem. And I think most students might respond better to that. I've been enjoying teaching a course that's just scratching the surface of that by asking about music and what can we learn about how music works by studying physics of music. And it's been a lot of fun to do it that way. The other point, I think, is that a lot of what science is doing isn't just showing you, what have we learned about the world, but it's been showing you an approach to how you solve problems in the world, whether they're scientific problems or not. And I think that actually is something that would be perhaps even more important to teach than physics to the vast majority of citizens, to have that extra tool as a way of asking questions about the world.
Some thoughts from you, George, on this?
Yes, and sometimes you give what you think is a brilliant and exciting lecture, and then the students say, will that be on the exam? Right? So sometimes you do that. But what I found is, it depends on the course, but if you involve the students in the projects and so forth, they can do that. So in that little video you saw the transit of Venus, which happened earlier this year. And I gave a project to my students, Eric Linder, who was also in there, and I co-teach a course called The Universe and Myself, and we show people how, we give them a basic overview of the physics and the universe and how it relates to, how they're actually, how people's individual lives are actually tied to the universe in ways they never expected, right, just in terms like that. And I gave to my students a project to watch the transit, to make an apparatus and take a picture of their apparatus and then a picture of the transit and so forth. But I also went to the Seoul High School of Science and set them up to measure the...
You mean in South Korea?
In South Korea. To measure the distance from the Earth to the sun by using the transit of Venus. And what they had to do was contact some other high school in another location and get their data so that you can measure the distance between the angle on the sun between points. And so that was the first big step in measuring the scale of the universe, was measuring the distance to the sun, and everything else scale from that, right? Mm-hmm. And so that was and the students got incredibly excited about it. And the KBS, the Korean broadcasting system, which is their public TV, actually came and filmed the students, me giving them a lecture and then giving them a charge to do that, and them going out and making the observations, and then coming back and having them report to me the various stages of them actually figuring out how far it was. And that was an incredibly good thing. And they filmed it all, and they're making a TV program out of it, and hoping that will show people that we had a lot of fun, because the students just got very excited about it. It was sort of like, whereas my students in my college course, only about a third of them actually went in there to get the credit for doing this project. And some of them did an interesting kind of job. But your lives get busier as you get older, and you get the fun driven out of you some. But in fact, there's no reason why science shouldn't be a lot of fun in grade school, through high school, and early college. It actually can be made very interesting for people, and you just have to show them some interesting things and let them do some calculation themselves. So one of our colleagues, that I've been supporting for a while, we have a hands-on astronomy where there's an automated telescope, which was one of Saul's early ideas. It spun off from the early supernova search. This automated telescope, and the students from the high school can call in and schedule an observation of an object, get pictures of it, and then analyze it. There's software that they can download, and they can do it. And we've had them discover asteroids and comet and one supernova. I can't remember, maybe there's two supernovas. It's been a very successful program, and we're actually running a version of it in Kenya now, which is quite spectacular, because up until then, there were no high school science courses in Kenya at all, right? So people get excited about this kind of stuff because they get their hands on it, right? That's the critical thing.
Oh, you got a lab in Moscow. I mean, let's talk about the research each of you is doing now and where this has all led you or taken you. I mean, with the Nobel Laureate on your shoulders and all of that. Saul, what are you doing now?
Well, the next question, of course, that we've been working on ever since the discovery has been trying to develop this next series of experiments that could get at why is it that the universe is accelerating. And of course, these are all international collaborations. There are now several different techniques to get there. We did the original measurements using supernova explosions as these marker points across the universe. And that's going on. That will continue on that approach. But by now, there's 2 or 3 other ways of going at it. And each one of those requires this large collaboration. Experiments are being built. In fact, some of the first data is coming in even this last year from some of those experiments. And so it's a really exciting period, actually, in this field.
And George, I want to hear about your research, but first we should mention I had Mickey Hart on my radio program, and there's been some collaboration with Mickey Hart that maybe you might want to talk.
Well, people just get carried away with everything. All right, well, I'll try and get to that. So I'm continuing to do research on the cosmic microwave background. So I have the difficult task of spending a lot of time in Paris because, well, I do some work there. I do a fair amount, actually. But the Planck satellite, which was the 3rd generation cosmic microwave background satellite, the early operations it was launched by the European Space Agency from French Guiana, and the early operations were done out of Paris. And so I agreed to come there for 6 months during the early operations because I was the person who had the most experience with running satellites before that. And of course, fortunately, there were almost no problems, and so that left me time to do other research. But we're getting to the point now where we have 2 full years of data, and one of the instruments has run out of cryogen cooling. And So, but we're getting ready to release in the next 6 months the cosmological results from that satellite, and there'll be some additional ones in the future. So we're coming to that, and we're already thinking about the next, one more, because we're never satisfied. But mainly because it's been extremely rich in terms of what it's telling us about the universe. So I'm continuing that, but there's a problem in the US and Europe that the budgets were growing and people got ambitious about what satellites they could do, and then the budgets stopped growing, and the pig was in the python, and it stopped everything from going. So John Mather, my co-winner, he's got one of the pigs, which is the JWST, that's stopping any astrophysics satellites from.
Because you weren't kidding before when you were talking about concerns about funding. There really are.
Right, and so I've been searching around for launches, and people get very upset if you go to China or something like that. But Russia has a lot of rockets, and we collaborate with the Russians, and they send our astronauts to the space station. So I wrote a proposal, and I got a large grant to be in Russia to do a satellite. So we have built a small satellite, and we're waiting for there's like 9 different instruments on the satellite, and 2 of them are to look for gamma ray bursts, which are the most powerful events that happen in the universe since the Big Bang. They're essentially when a star collapses, or something collapses into a black hole, and there are relativistic jets of material come out. You get about a solar power of energy out anywhere from a second to 100 seconds. I mean, it's just incredible amount of power, and you can see them across the universe. So they're potential tools, right? And they're like, some of them come from supernova, and some supernova have and some don't. But some of them we don't know what they come from, and we want to find out. So this instrument is a pathfinder to see if we could do a bigger mission to use these, because you can also test general relativity and the strong field limit, but you can use them as cosmological probes. And so I got this big grant. It's called a mega grant, because that's, the Russians are in the same kind of naming. There's a lot of similarities between the Russians and the Americans. They like to name things big things, right? There's the next, and there we started this lab, and we're trying to think about a next generation satellite. Now there's a power transition going on in Russia, and they're trying to privatize the space business. Before it used to be when you were approved, they just did it, right? Which is great, right? But now, if you're going to get approved, then you're going to have to find money to pay a private company to do some of the integration. So it's getting tougher, right, in the world. But we're trying to put together a satellite there with the scientists and get a Russian launch, because that's one of the few opportunities.
It's nice to have that kind of collaboration.
Right. There is a dark energy satellite that Saul and I are involved in that will be by ESA, but it's not till 2020 nominally, but I think 2022, right? That could be the end of the world. I mean, 222. It's like the devil's numbers or something like that. But
are you finding money harder to come by too, Saul? I mean, even with I know Nobel laureates who claim even with a Nobel Prize, it doesn't necessarily open doors.
Yeah, I think there was a time when if you had a Nobel Prize, you could walk into NASA and ask for a satellite, and it worked. I can report that no longer is the case. And of course, NASA's having a very difficult time now trying to figure out, how to build the next generation of programs that they would very much like to do. In some sense, it's a period in which we have to once more make the case for why is it that we do this basic research in a society where the taxpayers, they'll have to have a reason to pay for basic research. And I've been trying to look back through the historical story just to help tell the story. And it's very interesting because you see all these examples where people were working on something that seems completely impractical, where you can't imagine how it would ever help us in any particular way, from Kepler measuring the positions of planets. I guess unless you're an astrologer, you might think it would be helpful. But these lead to the Industrial Revolution. In the case of Einstein's theory of general relativity, there was a theory which was asking things about situations that we'd never expect to be in, where clocks would travel near the speed of light, things of that sort. And you can't imagine it would be practical. And yet, it turns out that the entire industry of the GPS and all the things that have been built around GPS location wouldn't work if you didn't have Einstein's theory of general relativity to make the small, precision corrections.
And since we're back on Einstein, I have to ask you both, are we any closer today or feasibly moving in on a unified field theory?
You mean a grand unified field theory?
Well, what Einstein envisioned, you know, I mean,
Or just a regular run-of-the-mill field theory?
rudimentary.
I mean, I think we were hoping that the dark energy would be a crack,
Yeah.
you know, that might allow us to get that to work, just because it seems to be something that is right at the borders between the forces and gravity, which is what you need to bring together to get a unified theory. But so far, of course, we don't know the answer.
Well, that's what string theory took to be their ambition, and I think of string theory as like a beautiful haiku. It's this poetry where everything had to just fit, and at the beginning it was just a beautiful idea that you'd only end up with one free parameter, and that's the free parameter that gives you the physical size of things. In the end, it's a string tension, but eventually in the end it would become our unit of measurement, and that you'd understand everything. You wouldn't need all these other constants we have because you'd understand they all came from this one single thing. And that was a great kind of thing, and then they run into problems, but they needed 10 dimensions in order to fit all these things together. And it only would work in 10 dimensions until they started realizing you didn't have to do the string. It could be a brain, it could be 10 or 11, right? And then there's a set of stuff. And that was good until they went and talked to the mathematicians, and the mathematicians said, well, you know, if you have 10 or 11 dimensions, there's 10 to the 500 ways of, you know, that's 1 followed by 500 zeros. It's a lot of ways that you can connect those ways. You don't just have to make a little cube in 10-dimensional cube, right? And you can identify the edges in very many complicated ways and twist things around. And there's a whole complicated geometry that the mathematicians have been worrying about for years. And that's too many degrees of freedom, right? And so that's why we're not so thrilled. I mean, I thought string theory was too mathematical at the beginning, and I thought, oh, they've made a breakthrough. They're going to, and then I thought they've made an anti-breakthrough, because they got too many degrees of freedom, right? And we used to joke that if I have 7 parameters, I can fill an elephant and make its trunk wiggle. You know, if you have too many degrees of freedom in your theory, you can make it fit any set of observations, right?
Well, as you mentioned geometry, we know that the universe is Euclidean, right?
The universe is very close to flat. And we know that from the cosmic microwave background measurements, because you can look for the ripples across the space.
Go anywhere.
And see the size. Right? And you see they're incredibly small, and in order for them to eventually grow over time, it has to be near the flat density for that to work. So you just think about a comb where all the things are going up, and now take that, and that comb represents flat space. If you wiggle it slightly, some of the tines will come together and some will go apart, and you'll get galaxy clusters and voids, but you need it to be very close to flat. And so when you make the observations in several different levels, you see the universe is on the global scale very close to flat. That's not saying it's exactly flat, because you have to keep making better and better. You have to keep employing us for millions of years, at least till the sun boils the oceans.
You probably should be clear when you say flat. You don't mean flat in a pancake sense. You mean
I mean flat in the sense that
Not like the flat Earth, no.
no, I mean flat in the sense that if you take a ruler and it goes in a straight line, and when you send the light beam, you see there's no curvature to it, right? Whereas in the surface of the Earth, if you could measure precisely enough, you would see the Earth's gravity curve that laser beam a little, right? So space around the Earth is slightly curved. Space around the sun is slightly curved. So the light from a distant star gets slightly bent going around, right? And you can see gravitational lensing where you see a star on both sides of a heavy object. But those are places where space is curved, but if you average over all those little bumps, and they turn out to be really tiny bumps, you find that the universe is, the light pretty much goes in straight lines over great distances, right?
Well, let's bring up our house lights, and
it's time for the quiz. That's the other way you get people interested. You tell them if they don't ask good questions, there's a quiz.
Actually, all you need to do here is raise your hand, and we'll come to you if you have a question or something you'd like to bring up to either Professor Smoot or Professor Friedlander.
No, sorry, Perlmutter.
Perlmutter, excuse me. If you have something, please just raise your hand, and please don't feel inhibited to do that.
This first question comes from your right in the orchestra.
Where's the orchestra?
So,
over here?
So during the talk, Dr. Perlmutter, you mentioned that the supernovae are the standard candle that was used for the determination of the accelerating universe, and the current work is using some other observationals. Could you just say a little bit more about the other observationals?
So the supernova is still in the game. We still use those to map out the expansion history of the universe at more and more precision. But there are at least a couple of other techniques now that are making a big difference. So one that's just recently gotten onto the table that we actually have some of the first measurements from just this past year or so. If you imagine that leftover hot and cold spots from the Big Bang that George was describing, that glow from the Big Bang, and they represent slight overdensities and underdensities in the very, very early universe. Now, over the billions of years since that time, those overdensities are where more of the galaxies formed, and the underdensities are where fewer of the galaxies formed. And so what people do is they now measure what's the average typical distances between galaxies in more recent times. And comparing that to those ripples in the very early universe tells us something about how the universe must have expanded since that very early time to the more recent times.
This question comes from the back right of the balcony.
What have you dared imagine is beyond the boundaries of the expanding universe?
I'm sorry, could you repeat the question?
She wants to know what's past the boundaries of the expanding universe.
No, it's more, what have you imagined is beyond the boundaries of the expanding universe?
Okay, so these guys, they're multi-universe guys. I'm the old-fashioned conservative guys. I think what we got, by definition, the universe is everything. And the simplest version of the universe, if it's flat, is it's infinite. But I don't even have a problem with a slightly closed universe, which is finite in size and just getting bigger with time. And will eventually get to be infinitely big. There doesn't, the example that I would give is imagining a perfectly spherical Earth with no oceans to worry about, and you're trapped to be on the surface of the Earth. Where's the inside and the outside of the Earth? Well, you're on the surface. You go around, there's no edges, there's no nothing, right? I mean, now you have to think about that in one more dimension, right? And just now imagine that the radius, this three-dimensional sphere is expanding, three-dimensional surface, right? So you can't imagine. The two-dimensional surface is just expanding with time. That's our expanding universe, and how it expands with time, that tells us the dynamics of the materials that's inside of it.
She was
so
really
I don't have
giving
that
a very
trouble.
challenging question there. How do you imagine what's beyond?
I'm the conservative, so I don't got to worry about what's inside or outside. I mean, I don't got any inside or outside. I got all there is.
But
Now, these guys, they have multiverses. You can talk to them.
I'm not particularly...
I'm not so sure I'm a multiverse. I remember that old cartoon in the New Yorker where the guy gets these signs that say, "This is the end of the universe." Really, you can't go past here. This is the end. This is the terminus. There's no movement beyond here. But it's because we can't imagine what's infinite. It's really beyond our ability.
I mean, the interesting thing is that I think that the infinite universe is mind-boggling, but I don't think it actually is the interesting part of your question in some sense, because the infinite universe we think of as being very similar. The picture we have is that as far as you go, it looks a lot like it does here. Still the same McDonald's, you come along. So I don't think that's the interesting part of your question. I think the more interesting part is that in an infinite universe, or even in a very, very large universe as we actually can see, I mean, it's not even the infinite part, it's just the part that we see, there's so many possibilities for how things could evolve and appear around stars and clusters of galaxies that it's I think even hard to picture what could be out there that we may that we would never be able to even come across. And in fact, that's my biggest disappointment, is the fact that the universe is so big that there's a good chance that we'll never really get the fun of trading photographs with our neighbors in the nearest supercluster of galaxies.
Well, I trust that first of all, everybody can say, even if you missed the ball game or the debates, we learned a hell of a lot this evening, didn't you? And we owe that to Professors Perlmutter and Smoot, and you've been a most attentive and gracious audience. Thank you. Thanks to George, and thanks to Saul.
Thank you.